Welcome to the second session of Lightning Talks on Fairness in AI Systems. I'm Amit Sharma, Senior Researcher at Microsoft Research in India, and I'll be your host. These talks cover mitigation strategies for fairness-related harms and the research questions that come up in the process of working on fairness in AI systems. We'll start with the topic of fairness in recommendation systems, then present how checklists can support fairness in the AI lifecycle, and finally discuss research questions on the challenges of measuring computational harms and the trade-offs in choosing an appropriate fairness metric. With that, please welcome Kinjal Basu to kick us off.
Hello, everyone. My name is Kinjal Basu, and I'm currently the tech lead for responsible AI at LinkedIn. And today I'm going to talk to you about how we can achieve fairness via post-processing for web-scale recommended systems. And this is a joint work with my co-authors, Preetham, Cyrus, Heloise, Divya, and Nurdin. So I'm going to base my talk on a very concrete example, and that is the connection recommended systems at LinkedIn. So if you're unfamiliar with the product, it's basically when a viewer comes to our platform and he or she gets to see a set of members that is recommended to him to connect to. Now, the way the flow works is that you can start by sending this person an invite, the invite gets received, and once that is accepted, then an edge is formed and you can start having conversations on with these two people together. So the major question that we want to ask here is that what is the fairness criteria for such a score-based ranking or recommendation system? Now, the major things that we look at in literature are basically things like demographic parity, predictive rate parity, equality of opportunity, and equalized odds. You can think about these metrics as some things around independence. So let's say we have a binary response Y, a prediction score S of X, and a protected attribute C. Then all of these metric definitions are basically some forms of independence of either the response Y or the score X, and we want it to be independent of the protected attribute C. Now, in this talk, we're going to focus on just the equality of opportunity and equalized odds and how we can build in post-processing systems to cure for these metrics. So what are the mitigation strategies? So we are actually looking for post-processing solutions, which means that we are trying to find a function f that takes the original score S of X and transforms it to f of S of X. And what that does is that we want to make sure that that transformed score actually satisfies the fairness criteria. And we want this function f to be feasible, but not just that. We also want it to optimize on model performance. And because this is a ranking system, position bias plays a very important role, and we do pay careful attention towards that. So if we want to solve for equality of opportunity, we choose the function f to be the cumulative distribution function of the score corresponding to this particular group. And we are showing in the full paper how that, by just choosing that, we can satisfy the equality of opportunity. Moreover, this is a monotonic transformation, which means that the ranking for each group actually remains unchanged. Finally, for equalized odds, the function that we choose is basically that it's a function that tries to make sure that the transformed score is as close as possible to the original score while maintaining that the equalized odds constraints are actually met. And we have shown in the full paper how this can be solved as a linear program. So lastly, I would briefly talk about some of the results. We first started with some initial experiments on simulated data that's shown on the right. So we created two different data sets where the score distributions for the two groups, 0 and 1, are kind of separate, shown in red and green. But after we apply, let's say, the equality of opportunity re-ranker, we see that the positive scores for y equal to 1 actually gets very well balanced, but not the negative. But when we apply for the equalized odds, it acts on both the y equal to 1 and the y equal to 0. So now let's look at how we actually apply this on a real-world experiment. So on the PYMK or connection recommendation problem, we choose the attribute C to being the infrequent and frequent members. So infrequent members are those people who come to the platform less and as a result are kind of underrepresented in the recommendation system. And frequent members are those who visit the platform a lot more and as a result are kind of overrepresented. So what happens is that because these frequent members are kind of overrepresented, they get to see a lot more invitations coming to them. And that's what makes this overall thing a rich getting richer kind of an effect, which we kind of want to nullify. So we choose our label as invitation sent. and choose the score as the scores of the top 100 positions. And we launch both the experiments, equality of opportunity and equalize odds. What we see from the reports is that both the sent as well as the accepted metrics have improved for the infrequent member, while we kept neutral for the frequent member, which means that we did a really good job of actually showing or sending more notifications or more invitations to the infrequent member while keeping it neutral for the frequent member. And with that, I want to end because of this short time. If you have any questions, just feel free to reach out to me. Thank you so much. The full paper link is given as well. Thank you.
Hi, I'm Michael Medeo, and I'll be speaking about our research on co-designing checklists to support fairness throughout the AI lifecycle. As has been widely reported, AI systems can lead to a variety of fairness-related harms, including representational harms such as demeaning or stereotyping, harms of allocating resources or opportunities, and harms related to disparities in the quality of service provided by an AI system, all of which may disproportionately impact already marginalized groups. In 2018, Microsoft took steps toward addressing these challenges by announcing 6 AI principles, including fairness and inclusiveness. And in the larger community, many tools and resources have been developed to help AI practitioners address fairness-related harms, including resources such as checklists for ethics in AI and data science. But few of these appear to have been designed with input from the teams that are intended to use them. In other fields, when checklists have been introduced without involving practitioners in their design, they've been misused or even ignored. Surgeons initially refused to use surgical checklists, while commercial airline pilots misused pre-flight checklists, resulting in catastrophe. To address this gap, we first investigated what AI practitioners' processes are for identifying and mitigating fairness-related harms. We then explored what they wanted out of a checklist for fairness in AI. And finally, we co-designed such a checklist with practitioners to support fairness throughout the design and development lifecycle. To do this, we conducted semi-structured interviews and co-design workshops with 48 industry practitioners from 12 technology companies in roles such as data scientist, machine learning engineer, designer, and product manager, among others. In these workshops, participants suggested checklist items for various stages of a typical AI lifecycle and iteratively provided feedback on the items suggested by others. First, we found that industry AI teams mostly have unstructured approaches to addressing fairness, often driven by individual advocates. But this individual advocacy may be difficult given organizations' incentives to ship products on rapid timescales, and due to the social dynamics of teams and organizations that may inhibit advocacy. Practitioners felt that having a formal process for fairness could empower team members to identify potential issues and help teams negotiate priorities, but only if it fit into their existing workflows. And they felt that these checklists must be supported by an organizational culture to drive adoption, including integrating into organizations' goals and priorities. Following the co-design workshops, we ended up with a checklist to address fairness-related harms across 6 phases of AI development, beginning with envisioning a potential system and potential fairness-related harms, including asking whether AI was needed at all, to defining model and data requirements, as well as defining what fairness means for a particular societal context, and defining criteria for measuring fairness and fairness-related harms. This also includes items for prototyping and building models, including prompting teams to develop approaches to identify and assess fairness-related harms, such as measuring performance disparities with disaggregated evaluations, for instance, as well as prompting teams to consider certain things before launching and while monitoring ongoing system performance after deployment, including developing methods for stakeholder feedback and considering how performance may be impacted by the deployment context. And this checklist is available on Microsoft's Responsible AI resource page, and we encourage you to download it and use it in your work. Finally, it's worth noting that participants were concerned that checklists may lead to rote compliance, given that fairness in AI is deeply contextual for particular societal contexts and often contested by stakeholder groups in those contexts. As such, practitioners often wanted to be given or to develop a general checklist and then to adapt it to fit their workflow. We're conducting ongoing research into how teams may customize such a general checklist. If you're interested in learning more, please read our Kai paper on this research or feel free to reach out. Thank you.
Hi, this is Alexandra Olteanu. The question of foresight and measurement of possible computational harms that existing AI technologies may replicate, exacerbate, or even cause is critical to building responsible technologies. To effectively measure such harms, however, we first need to determine what exactly we should be measuring. That is, we need to identify what harms are possible, how severe those harms are, and who is likely to be adversely impacted by them. Having clarity about what we need to measure will enable more effective measurements and mitigation strategies. However, there is a tendency to start with the mitigations of harms without a clear rationale for how those issues were identified, many of which end up being poorly articulated, poorly understood, and poorly operationalized notions of what constitutes bias, unfairness, or stereotyping. This is in part because, as researchers and practitioners, we may fail to recognize that when we try to anticipate harms, a key challenge is often overcoming our own failures of imagination. Doing better requires challenging assumptions about what is measured and mitigated, communicating no limitations of not only AI technologies, but also of harms measurement and mitigation strategies, and clearly articulating competing goals and constraints. This can in turn inform the development of frameworks to better identify possible adverse impacts. To develop better measurements, we can also turn to measurement practices from social sciences, where a clear distinction is made between what should be measured, or what is the unobservable phenomenon of interest, and what are the observable properties related to that phenomenon that we could use to operationalize its measurement. But let me use a few examples. I'll focus on open text generation applications like making textual suggestions to assist users in replying to emails or in searching for information. Such open-ended generation settings makes it particularly hard to effectively identify problematic outputs. This is because many problematic scenarios are context-dependent and generally elusive. Consider these examples of search query completions. None of them contain profanity, hate speech, or reflect sexist or racist views. What makes them problematic is the context in which they were presented. For instance, contagious is an excellent suggestion for the flu, but not for cancer. Effectively avoiding such cases and setting clear boundaries around the space of problematic suggestions is difficult due to the long-tail nature of writing tasks and variations in data quality and how people assess potential harms. Indeed, by examining when search query suggestions might be problematic, we found that contextual factors like who is seeing the suggestions, what user input a suggestion was generated for, as well as factors surrounding data availability, all contributed to how problematic a suggestion was deemed to be. This is the case even for applications where the suggestions are curated. Take this example of highly positive, life-affirming candidates for email reply suggestions. It's unlikely that offensive responses would be surfaced here. So what could the issue be? As this email vignette shows, not all scenarios call for life-affirming answers. None of these suggestions are appropriate for such an email. In fact, in another study, our participants voiced concerns about several types of reply suggestions, including dissonant suggestions, but also gender-assuming, unprofessional, cultural mismatches, overly positive and confusing, and impolite suggestions. But even if we know what harms are possible, measuring them can also be challenging. Let's look at existing efforts that use benchmark datasets to quantify computational harms like stereotyping. Such datasets often consist of test pairs of stereotypical and anti-stereotypical sentences to probe language models' relative preference for stereotypes. They do so by counting which sentence is more likely for each test pair, obtaining a perfect score when a model prefers stereotypes 50% of the time. This perhaps is intuitive. So what is the issue? Consider this example. intended to help test for stereotypes about race, and where given a context sentence, I really like Norwegian salmon, the test then checks if, for a given language model, this sentence is more likely to be followed by the sentence marked as stereotypical, the exchange student became the star of our art shows, or by the anti-stereotypical version, where the student was the star of the football team. One might quickly notice many issues related to both what this test is attempting to measure and what is actually measuring. For instance, the Norwegian salmon is not really a historically disadvantaged group. Norwegian is misspelled, and it's also unclear which sentence a good language model should prefer here. This example is not isolated. Examining existing datasets, we found cases where all test pairs were affected by at least one of these issues that we identified. Thank you.
Hi, I'm Amit Deshpande, and I'm going to talk about a fine balance, individual fairness, and group fairness. The agenda is to tell you about a tale of two fairness metrics, inframarginality and underranking. These are new proposals to quantify individual fairness in classification and ranking. And we will see interaction between group fairness and inframarginality, and also group fairness and underranking. Fair classification and ranking has been a well-studied problem, but a lot of focus has been on group fair classification and ranking, where the notion of fairness is typically outcome-based, for example, equal false positive rates or equal accuracy across groups. It's also common to use representation-based fairness, for example, demographic parity or minimum representation guarantee among the top ranks. Is a random classifier fair? A random classifier is group fair because it gives equal outcomes for two groups, for most outcome-based notions of fairness. But it is individually unfair because it treats high-risk and low-risk individuals similarly. Another question that got us thinking was, is group fair re-ranking anti-meritocratic? So group fair re-ranking or post-processing for group fair ranking, it maximizes aggregate ranking utility while maintaining a certain minimum representation guarantees for groups in the top ranks or sometimes in the top prefixes. So one question that we thought about was, how much do group fair re-ranking algorithms underrank individuals compared to their true rank or compared to their peers? The first question led to this interesting notion called inframarginality audit, or inframarginality as a definition for individual fairness, and inframarginality audit of group fair classifiers. Inframarginality quantifies how much a classifier deviates from a threshold classifier on the true risk probability of individuals. Many times in group fairness or in general in classification, the classifier outputs a score which is supposed to mimic the true risk probability of individuals. And inframarginality quantifies how much a classifier deviates from a threshold classifier on this. In this sense, base classifier that maximizes accuracy has zero inframarginality with respect to threshold half, whereas a random classifier has high inframarginality with respect to any threshold. We can do inframarginality audit, and what surprisingly we found was that some state-of-the-art group fair classifiers can have very high inframarginality, and inframarginality audit also gives a way to choose among multiple group fair classifiers. A paper on this appeared in FORC 20, and you can check out the link to the talk video at the bottom. So this is what we found, that when we do inframarginality audit, we often can do it even with good estimates of the true risk probabilities. We don't need the actual true risk probabilities. And under reasonable assumptions, the inframarginality audit still makes sense. And we observe that some state-of-the-art group fair classifiers can have inframarginality nearly as high as that of a random classifier. So one must be careful in choosing the mitigation toolkits in fairness. The other part that I want to talk about is on the problem of underranking in group fair ranking. We define underranking as the worst case multiplicative displacement of an individual's 2 rank in a re-ranking, especially in the case of group fair re-ranking. And we look at the trade-offs between group fairness and underranking. We show lower bounds on the optimal trade-offs between group fairness and underranking. And we give an efficient re-ranking algorithm with simultaneous underranking and group fairness guarantees. A paper on this appeared in ICML this year. It's joint work with Shruti Gorantla and Anand Lewis from IISc, and the talk video you can check out in the link below. The experiments that we did, there we found out that our algorithm, when compared to other group fair underranking state-of-the-art algorithms, we get the best of both worlds in terms of underranking as well as group fairness, and we have a much faster running time than the baselines. I will end my talk here. Here are the links to the papers that you can check out. Thank you.